Welcome to our video today that we're going to discuss a specific type of function called radical functions. We're just going to add this to your list of functions so you get some information on its shape, its appearance, and then we're going to apply what we know about transformations to this specific type of function. So for example, at this point in grade 10, you've studied linear functions, right? We know that that would be something like y equals x plus 2. We've studied quadratic functions. We know they look something like this. Y equals negative x squared plus 4. I knew this was linear because x and y were the first. I knew this was a quadratic because my x was squared. Well, a radical function, now primarily square root functions. There could be cube root, fourth root, etc., etc. But we're going to look at the specific version of square roots. Well, they're going to be easy to pick out because they will have a square root symbol on them. So given a linear function, the base function was y equals x. Given a quadratic function, our base function was y equals x squared. So we kind of use that as our reference. The reference for radical functions is the function f of x equals the square root of x. Now, there's a few ordered pairs here just to kind of show you what it would look like. If x was 0, imagine I'm substituting in here. X is 0, you get 0. If x is 1/4, the square root of 1/4 would be 1/2. So when x is a quarter, you're at 1/2. If x is 1, the square root of 1 is 1, so you have 1 comma 1. Square root of 4, so if you go way over here to 4, you'd be up at 2. 6, the square root of 6 is 2.4. The next one that would have a nice integer or a natural number answer would be the square root of 9. So if x was 9, y would be 3. And these would be some ordered pairs. Now, if I was going to do a mapping or something with this, I'd probably stay away from the fractions unless I had to. So I'd probably go with a set of points that went like 0, 0, 1, comma 1. And then I'd go 4, comma 9. 4, comma 2, getting ahead of myself. 9, comma 3. If you needed any more than that, the next one I would go with would be 16, comma 4, 25, comma 5. And remember, reason is I want x values that are perfect squares so that when I take the square root of them, I get nice numbers like I did here. Now, I've got a few properties that would have to hold true for this function coming up on my next slide, but we'll just kind of look at this. Now, think about if we're taking the square root of a number, one thing we're going to always make sure that this is going to have to turn out to be a positive answer. So that's going to tell me that all the y values in this graph are going to be above the x-axis, which means my range should be anything that's bigger than or equal to 0. It could be 0, but I could never take the square of a number and get a negative value. My domain, now note the x is underneath a square root sign. We cannot take the square root of negative numbers. Therefore, the x values must be bigger than or equal to 0 as well. So if I just kind of look at the summary of the properties of this function, so this is your base function, y equals square root x. The left endpoint is at 0, 0. So this graph does not go past here. It stops right there. Now there's nothing to stop us from picking more x values, so this graph continues at the right endpoint. So it says no right endpoint. It has the appearance of a half parabola opening to the right. The domain, I've already talked about that, and range. You can apply your transformations much like you would have with regular functions. So if we look at this function right here, y equals a, y equals a, b, x minus h, and then the plus k is out here. Well, I say this is a transformation of the function y equals the square root of x. And if you say, well, what did we do to that base function? Well, let's summarize it in a mapping. This is what we did to every single ordered pair on that graph. Now, compare this with our function notation where we went like g of x, g of x equals a f at b, x minus c, close that off, and then plus d. So it's the same idea. So this stuff is inserted in where the x is. That's this stuff here. These two transformations are on the outside, which would be this one and this one. Okay, so these are going to affect the x's. Well, we're going to multiply every x by 1 over b. Remember, this one's always the reciprocal. We are then going to take all the x's and move them right h. We're going to multiply every y value on the base function root x by the number a, and we're going to move them all up k. So what you know about transformations obviously doesn't disappear or change because we're talking about a square root function. Those transformations hold true for every type of function. So we're just kind of throwing you a new one here, which is a radical function, just so you know what they look like, as I said, and you could apply some transformations. Now, if I looked at this function and I identify my transformations, so let's go g of x equals -5. Now, much like in function notation, this is not the way we want to present it. We want x minus 2, and then we want our plus 1 out here. So if I identify the transformations in words, we are going to reflect. So when the negative's out here, that's when your y's switch from positive to negative or vice versa. We're going to reflect it in the x-axis. That takes care of the negative. We're going to stretch it vertically by a factor of 5. Vertically by a factor of 5. Meaning multiply every y by 5. We're going to take a third of all the x values. So take 1/3 of all x values. That's called a horizontal stretch, which in this case we might classify as a compression. So horizontal stretch. It's going to shift to the right 2. That's a horizontal translation. So right 2. And then we are going to move it up 1. So that's identifying all of our transformations. This says use this mapping to develop 4 ordered pairs that could be used to sketch g of x. We're going to write a mapping here first. We're going to take, we said, a third of all the x's, and we're going to move them right 2. We are going to multiply every y value by a negative. That'll reflect them, and we're going to stretch them by a factor of 5. So -5 multiplied by all your y coordinates, and then we're going to move it up 1 as well. Now it says to use 4 ordered pairs. Well, what you'd want to do here is start with your base function, which is y equals radical x, so that's your base, and get 4 ordered pairs that you know would clearly be on that point. Now this is a good one. You want to know that's kind of that end point, so you definitely want that one. 1, 1 would work nicely. 4, 2, and let's go 9, 3. Apply our mapping to each one of these points. So this is going to be now on our new function. This is where these points will be. X, y. So 0, 0. A third of 0, and then add 2. That'll be now be sitting at an x value of 2. The y values, this will be 0 plus 1. So that's 2, 1. 1, 1. So a third of 1 is a third, plus 2 is 2 1/3, or 7 over 3. And the y value will be at -4. 4, 2. 1/3 of 4 is 4 over 3, plus 2. So 4 over 3 is 1 1/3, so this is 3 1/3. And the y value will be -9. A third of 9 is 3. 3 plus 2 is 5. And y value, which was at 3, is now at negative 14. Okay, so if I take these, and I'm just drawing a quick sketch here, nothing fancy, and I notice the y's got to go down to negative 14, and my x's are going to start at 2. So remember, the original starting point is now going to be, which was 0, 0, but we've moved that to over 2, up 1. That's this point. So this is your new start point. So it's going to be here. And then it's going to be 2 1/3, negative 4. So this one was at 1. Let's say that's 1. Again, my scale is going to be a little wonky here. I need this to go down a bit further. And again, I'm not going to really scale it off. We're just going to eyeball and estimate what we get here. If we had some grid paper or something and we were more concerned, we're just going to try and get a rough shape of this. All right, so 2 1/3, this was 2, so 2 1/3 is right close nearby this, and it's at negative 4. Let's put that down here. 3 1/3 is at negative 9. My scale is terrible here. I should do a better job of this. Just give me a second here. I'm going to get a piece of grid. All right, sorry about that. Once I got looking at it, my graph was just going to be it needed to be a bit more accurate. So with these radical functions, I think it's probably best that we slow ourselves down here and make a better graph. So I just wanted, once I've got it set up here, and I'll explain to you what I did. So I just grabbed a piece of grid paper, put it in behind. I made my scale here go by 2s on the y-axis because I knew I had to go down to negative 14. I made my scale on the y-axis, in the x-axis go in increments of 3. Now the reason I did that is because I saw that at a couple of points that had 1/3 in them, so that would give me an easy way to plot these points. So let's see what we can come up with here. So 2, 1. 2, 1 would be there. So that's our new, was 0, 0. 1, 1 is at 2 1/3, negative 4. So 2 1/3, negative 4. 3 1/3, so 3 1/3 is at negative 9. So 3 1/3 is there, and 5 is at negative 14. 5 is at negative 14. So this was my start. There's my graph. Now, I intentionally waited until I looked at this graph. Some of you might have thought up here I skipped over domain and range. I haven't. I think once I have the picture in front of me, my domain and range now should be easier to identify. So let's look at the domain. All the x values I can see are greater than or equal to 2. And now the range, all the y values are less than or equal to 1. Now I want you to notice that those corresponded with your translations. So when you're looking for your domain and range, in the beginning, remember, it was greater than or equal to 0, less than or equal to 0. And then when you move your point left or right, and then up, down, it will change your domain and range accordingly. Now, you're not always going to be sketching the graph, but in your head you can kind of play around with it and say, well, what's going to happen? I want to go this way. The key here was for the range, you had to realize that normally these graphs, you may say, well, aren't they supposed to go this way? They do, but remember it was reflected. So you got to make sure you pay close attention to reflections because it will impact your range. And if it had a reflection the other way, which went this way instead, then you could also run into a situation where this would switch to x is less than or equal to some number. All right, so looking at your transformations becomes very important when you're trying to identify your domain and range. All right, so let's have a look at this one. It's basically the exact same thing. So I've got g of x equals 2 square root take out your quarter. That'll give you x plus 8. Remember, when you take a quarter out, that means you're going to divide by 1/4, which is the same as multiplying by 4/1. And then you'll still have your minus 5 out here. Let's go right to our mapping. So I'm not going to write it out in words this time. So I am going to multiply all the x's by 4. I'm going to move them left 8. I'm going to double all the y values. And then I am going to subtract 5 off them. So horizontal stretch, horizontal translation, vertical stretch, vertical translation, no reflections in this one. So there was no negative here or here, so it had no reflection. Well, let's get our 4 key points. Now remember, the 0, 0 is kind of your key one to get your domain and range. I left it out like I did before, so let's go with 0, 0, 1, 1, 4, 2, and 9, 3. Put those through your mapping to get your new points. Minus 8, negative 5. That would be enough, actually, if I did nothing else. If I didn't have to draw this, I should be able to state the domain and range now, because think about what happened. You're going to take your base graph, which looks like this. It's not going to flip this way or down this way, so it's just going to simply, we are going to stretch it, but that won't affect your domain and range. What we are going to do is move it up, or no, sorry, down 5, left 8. So this point is now going to be situated, instead of 0, 0, it's going to be over negative 8, down 5. Still going to make that same shape. So now our domain, all the x values would have to be greater than or equal to negative 8, sorry, not 5. And our range, all the y values would be greater than or equal to negative 5. Now let's continue our mapping here for sketching purposes. So 1, 1 would be at negative 4, negative 3. 4 would give me 16 minus 8, so that would be 8. 2 times 2 is 4 minus 5, that's minus 1. And 9 times 4 is 36, minus 8 is 28. And my y value would be at 6, be a positive 1. Okay, I'm just going to go back here and steal. Alright, so I've got my grid back here. I just wanted to go back and get that grid. Now I'll kind of talk you through this time. So I put my axes on. You look your points over. So this is the new graph that I'm drawing, this one. So I need my x's to go over to negative 8, all the way over to 28. So I figure if I go by 2's on this grid, so negative 8 there, negative 6, negative 4, negative 2, 0. So now 2, 4, 6, 8. I'm just going to mark the ones I need. 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28. So there's 28. There's 8. I need my y's to go down as far as negative 5. Negative 1, negative 2, negative 3, negative 4, negative 5, and then I'm going to go up to 1. Okay, so let's put our new point. So 0, 0 is now at negative 8, negative 5. 5, which would be here. Negative 4, negative 3, which is here. 8 and negative 1, which is there. And 28 and 1. So it is giving us that nice kind of half parabola shape to it. This being our endpoint. Now let's think about what I said about the domain and range. So the domain, every x value is greater than or equal to negative 8. That's what I had. And the range, all the y values are up here. So they're all greater than or equal to minus 5. So mapping that point 0, 0 and figuring out where it's sitting, and then knowing whether your graph's reflected or not, will be the keys to determining your domain and range in this. All right, so that's all this section is. quite short, but it takes some of the things we learned about functions and transformations. It shows you how you can use a mapping to help you draw graphs. This is going to be a really important skill that we're going to use during multiple other sections in this course. So if this is something you're struggling with, it's really important that you do get this figured out, as not only for this section or this unit, it will be something that will be used, as I said, multiple places in the course. All right, as always, best of luck with your practice questions. If you do have any questions or concern, remember, you can put things or questions, pictures of work in your need help, and then let me know that there's stuff in there, and I'll have a look at it, and I can either respond in video or audio or just with some comments. All right, thank you, and best of luck.